Hello guys, I am Tarun from Chemical Department 2020 batch. Now we are going to discuss about fourth module of course ME1100. This is the course grading and exam timing. So the fourth quiz is on 28th June and I have divided this module into two parts. First part is entropy and second part thermodynamic cycles. So in let's discuss first part. So in first part, this is recap of is only for a cycle. Both the Kelvin Planck statement and Clausius statements are for a device that operates in a cycle. And in entropy, we often deal with process rather than cycles. So generally, here we are interested in processes. So this is efficiency of a heat engine. So we can write efficiency equals to 1 minus QL by QH. So 1 minus that is equals to 1 minus TL by TH. So only for reversible process we can write QL by QH equals to TL by TH, and the efficiency is the reverse of COP value. Now the COP of a refrigerator equals to QL by W input and COP of heat pump equals to QH by W input. So we can write COP of reversible heat pump equals to only for reversible heat pump equals to QH divided by W in equals to QH divided by WH minus QL. So that is equals to QH divided by TH minus QTL. So so and also we can write the COP value in terms of TL and TH of COP of refrigerator. Now for a reversible process, only for a reversible process, QH divided by QL equals to TH by TL, and now uh, QH divided by TH minus QL by divided by TL equals to 0. So in a whole cycle, del Q divided by T integration in a whole cycle of del Q divided by T equals to 0. So now let's discuss entropy. So entropy is an extensive property, a state function, and unit is kilojoule per Kelvin. And change in entropy equals to change in entropy from process 1 to 2 equals to integration of 1 to 2 integration of dq by t. So and entropy leads to make a qualitative analysis of process based on the second law of thermodynamics. For reversible adiabatic process, change in entropy equals to 0 because dq equals to 0 for reversible adiabatic process. Now entropy change for Carnot cycle. So in Carnot cycle, all processes are reversible, and net change in entropy for any reversible cycle is 0, and we know. And so change in entropy for Carnot cycle equals to also 0. Now the absolute value of entropy. So the basis to determine the absolute value of entropy is the entropy of a perfect crystal. Perfect crystal is 0 at absolute 0 temperature. So now places inequality. So for reversible cycle, change in entropy equals to 0 only for reversible cycle, not reversible process. And for irreversible cycle, change in entropy is equals to less than 0. So overall, Clausius inequality equals to change in entropy less than equals to 0 for a cycle. Now, entropy change in reversible and irreversible process between two states. So for state 1 to 2, we know W irreversible less than W reversible and delta U reversible equals to delta U irreversible because delta U is a uh, state function, not path function. So by first law, we can write Q irreversible less than Q reversible and delta S irreversible greater than delta Q by T and delta S reversible equals to delta Q by T. Now, isentropic process. So in a reversible adiabatic process, the heat transfer is zero. We know the heat transfer is zero and the So the change in entropy will also zero. So this process called an isentropic process. Isentropic process, it's been reversible adiabatic process, and the flow through nozzles, compressors, and the turbines is often take to be reversible and adiabatic. So these processes are also isentropic process. Now, entropy change during process. So for any process, delta S system equals to delta H due to heat transfer and delta S production. And where delta S production equals to entropy generated due to dissipative effects. Effect, it's like irreversibilities in system. And now entropy calculations for various process and substance. So for reversible process, we can write TdS equals to dq reversible, and by first law we can write dq reversible equals to du plus pdv. So replace dq reversible by du plus pdv, we can compute tds equals to du plus pdv. So this is the first equation to compute entropy, and we know h equals to u plus pv. So changing h dh equals to du plus pdv minus vdp. So by substituting the value of du, we can compute Tds equals to Ds minus Vdp. So this is the second equation to compute entropy. And these relations can be used for both reversible and irreversible process. Now, entropy change for an ideal gas with constant specific heats undergoing a process. So by using first equation to compute entropy, dTds equals to du plus pdv, we know, and we know dq equals to cv and ideal gas equation PV equals to RT. So we can compute entropy delta S equals to M CV ln T2 by T1 and RLN plus RLN V2 by V1. And by using second equation to compute entropy, we know we know dH equals to Cp dt and ideal gas equation PV equals to RT. So we can compute and change in entropy delta S equals to M Cp ln T2 by T1 minus R ln P2 by P1. Now, entropy change during entropy change in solid and liquids. So in solids and liquids, volume changes are negligible, and Cp and Cv are also equal. So Cp equals to Cv and is equals to C. And if change in temperature from 1 to 2 is T2 minus T1, so then entropy change equals to Mc ln T2 by T1. Now, entropy change in steam. So we can compute entropy change in steam by saturated steam table. Now, qualitative test for irreversibility. So for an irreversible process, delta S greater than 1 to 2 dq by T, integration of dq by T. For an irreversible process, integration of dq by T does not equal change in entropy, and for an irreversible process, entropy is greater than dq by T. So hence, entropy change for an irreversible process is the higher than the change in a reversible process for the same dq and t. So in irreversible process, change in entropy is greater than change in entropy in reversible process. Now, entropy generation. So only for an irreversible process, entropy generation is applicable only for an irreversible process. So entropy change in irreversible process, we can write ds equals to dq by t plus ds generation, where entropy generation is always positive. It can be zero, but it can't be negative. So where delta S generation is the entropy generated due to irreversibilities in the system, and dq irreversible equals to tds minus tds generation. And also we can write dw irreversible equals to pdv minus tds generation. Now, principle of increase of entropy. Let us consider a system and its surrounding. So, change in entropy in system greater than equals to dq by t, and for surrounding, changing for surrounding, dq will be negative. So, change in entropy for surrounding is equals to minus dq by t naught. Now, hence, change in entropy, so the net change in entropy equals to change in entropy in system plus change in entropy in surrounding. So net change is greater than equals to dq into 1 by t minus 1 by t naught, where t naught is the temperature of surrounding. So change in entropy, so the net change in entropy is always greater than equals to 0. Now, so this was first part. Now let us discuss part second, thermodynamic cycles. So in thermodynamic cycle, let us discuss about the TS diagram of Carnot cycle. So this is the TS diagram of Carnot cycle, and process 1 to 2 is reversible adiabatic compression 1 to 2, and 2 to 3 is reversible isothermal heat addition, and 3 to 4 is reversible adiabatic expansion, and again 4 to 1 is reversible isothermal but heat rejection. Now the steam cycle. So this is the arrangement of steam cycle. So this is the boiler, and this is turbine, and this is condenser, or and this is pump. So now this is steam turbine. Now let us discuss about steam turbine. Steam turbine, or yeah, gas turbine. So in steam turbine processes, so all processes are adiabatic. So and and change in potential energy and change in kinetic energy are also negligible. So by study flow energy equation, we can write Q dash minus W dash external equals to m dot into He minus Ve square by 2 plus GZD minus m dot into Hi plus Vi square by 2 plus GZD. So here change in potential energy and change in kinetic energy are negligible. So these terms become cancelled, and adiabatic process, so Q dash equals to 0. So now power produced by the turbine equals to W dash external equals to m dot equals into Hi minus He, and this is the diagram of turbine. Now heat exchanger. So in heat exchanger, change in potential energy and change in kinetic energy are also negligible. So by study the energy equation, we can write this, and here in heat exchanger, work done, external work done also 0. External work done is also 0. So rate of heat transfer equals to m dot into H minus Hi, and these are the there several, and here several type of heat exchanger present. So this is boiler and condenser and combustion. So these all are heat exchanger. Now water pump. So this is water pump. So water pump is in adiabatic condition, and here also change in potential energy and change in kinetic energy are negligible. And in water pump, change in specific volume is also negligible, and change in temperature is also negligible. So now let us apply steady flow energy equation for water pump. So we can write Q minus W this external equals to this, and these terms become cancelled. So power required by the pump equals to WP equals to minus W external. So that is equals to m dot into H minus Hi. Now next process involved in the steam cycle. So this is the arrangement of steam cycle. So in the path 1 to 2, here is isentropic compression 1 to 2, and 2 to 3 is the reversible heat addition transfer to the device, and 3 to 4 also this is isentropic but expansion, and 4 to 1 is also reversible heat rejection. at constant temperature. Now, ideal Rankine cycle. So this is ideal Rankine cycle. So cycle from 1 to 2s, 2s to 3, 3 to 4s, and 4s to 1. And heat addition in boiler uh, and heat addition to the in the boiler equals to QH equals to m dot into H3 minus H2S, and heat removal in condenser equals to QL equals to m dot into H4S minus H1, this one, and work done by the turbine equals to m dot into H3 minus H4S, H3 minus H4S, this one. And also we can compute work input to the pump, and net work output from the cycle equals to work input minus work output minus work input. So net work output equals to WT minus WP. Now efficiency of Rankine cycle. So we can write efficiency of Rankine cycle equals to W net output divided by uh, added heat QH. Now this is actual Rankine cycle. Actual Rankine cycle means path 1 to 2, 2 to 3, 1 to 2 here, and 2 to 3 here, and 3 to 4 here, and 4 to 1. Here same as we can write heat addition in boiler, that is equals to m dot into H3 minus H2, and heat removal from condenser we can write like this, and work done by the turbine equals to H3 minus H4, H3 minus H4, this one, this path. And work input to the pump we can write m dot into H2 minus H1, H2 minus H1, this part. And now we can write net work output equals to work output minus work input. So efficiency of actual Rankine cycle equals to we can write net work output divided by added heat. Added heat also is QH. Now in Rankine cycle, efficiency of isentropic pump. So isentropic efficiency of isentropic pump we can write H2S minus H1, H2S, H2S minus H1 divided by H2 minus H1 divided by H2 minus H1. This is efficiency of isentropic pump. So and also we can see from here, this is this difference divided by this difference. So this is also less than 1. Now the efficiency of isentropic turbine. So we can write efficiency of isentropic turbine equals to H3 minus H4 divided by H3 minus H4S. So H3 minus H4, this part, and H3 minus H4S, and this is also less than 1. Now open cycle gas turbine. So this is the arrangement of open cycle gas turbine. Here enters fresh air and here execute gas. And this is compressor, and this is combustion, and this is turbine. Now open cycle gas turbine. So these are some diagrams, these are some curve of open cycle gas turbine. This is PV curve and this is TS curve. Here heat is added and here heat is released, and this is isentropic path and this is also isentropic path, and we can write TS curve like this is constant pressure and this is constant pressure, this is constant entropy isentropic 1 to 2, so 1 to 2, and this is also isentropic 3 to 4. Now closed cycle gas turbine. So this is the arrangement of closed cycle gas turbine. So here compressor takes some input from heat exchanger, and turbine released some output to the heat exchanger. So this is closed from here. This is closed from here. So this is the arrangement of closed cycle, gas turbine. Now compression. So compressor is in adiabatic condition, and change in the compression, change in potential energy and change in kinetic energy are also negligible. So this is the arrangement of compression. So this is the arrangement of steam cycle, and here this is compression. So now let us apply the steady flow energy equation for compression. So adiabatic condition, so Q is equal to 0, and these terms becomes cancelled, and then power needed by the compressor equals to WC equals to minus W external equals to m dot into H minus Hi. Now this is Brayton cycle. So in Brayton cycle, this is path 1 to 2, 2 to 3, and 3 to 4, 4 to 1. And this is the diagram of Brayton cycle. So path 1 to 2 is isentropic compression, 2 to 3 is reversible constant pressure heat addition in the heater, and 3 to 4 is isentropic expansion, and 4 to 1 is reversible constant pressure but heat rejection. Now this is the TS diagram of Brayton cycle, and we can compute heat addition in the heater equals to m dot into H3 minus H2, H3 minus H2, and we can compute heat rejection equals to H4 minus H1, and work done by the turbine equals to m dot into H3 minus H4. And similarly we can compute some other quantities like work output, net work output, and efficiency equals to net work output divided by heat added, so W in divided by QH. And we can apply these equation for adiabatic path, adiabatic process, and we can write delta H equals to Cp into delta T, Cp at constant pressure. Now isentropic efficiency of turbine in Brayton cycle equals to H3 minus H4 divided by H3 minus H4s. So H3 minus H4 divided by H4, H3 minus H4s, and we can write isentropic efficiency of compressor in Brayton cycle equals to H2s minus H1 divided by H2 minus H1. Now vapor compression refrigeration cycle, and this is ideal cycle, and after we will discuss actual cycle. This is ideal cycle. So here path 1 to 2 is isentropic compression, 2 to 3 is reversible constant pressure and heat rejection, and also 3 to 4 is isentropic isenthalpic isenthalpic irreversible expansion in value. 3 to 4 3 to 4 is also isenthalpic. 4 to 1 is reversible constant pressure heat addition in the evaporate. Now, and this is the vapor compression refrigerator cycle. Vapor compression refrigerator cycle, and this is actual cycle, and this is ideal cycle. So here is some changes we will see. So heat addition in evaporate equals to m dot into H1 minus H4, H1 minus H4, and work output to the compressor we can compute, and isenthalpic efficiency of compressor we can compute H2s minus H1 divided by H2 minus H1, H2s minus H1 divided by H2 minus H1, and we can compute coefficient of performance equals to QL divided by WC. Now, so uh, this was part. This was fourth module of MA 1100. Thank you.